Hello everyone, this is Alex. We're going to present our work titled Pancreas Segmentation-Derived Biomarkers, Volume and Shape Metrics in the UK Biobank Imaging Study. Chronic pancreas disease, among them metabolic syndrome, type 2 diabetes, chronic pancreatitis or pancreatic cancer, are all rising with the increased prevalence in obesity. Obesity causes fat infiltration in the pancreas, and this leads to changes in pancreas volume and pancreas shape. We think that advanced feature extraction from pancreas segmentation masks may have potential in discovery, diagnosis, and monitoring of chronic pancreas disease. With regards to volume, pancreas volume has been reported to be smaller in diabetic subjects. The development of deep learning and convolutional neural networks have substantially improved automated segmentation and volume measurement of the pancreas. Attention-based as well as self-adapting network architectures have been recently presented with applications in pancreas segmentation. Now, the variation in pancreas shape, even in the nominally healthy population, makes segmentation of the pancreas a really challenging problem. With regards to shape, imaging-based morphology measurement currently relies either on subjective scoring of things like surface irregularity or on handcrafted, non-specific metrics such as the fractal dimension or organ curvature. Advances in machine learning invite a more data-driven approach to pancreas shape characterization. So the purpose of this work is to develop an automated pipeline for the measurement of pancreas volume and the characterization of pancreas shape using a data-driven approach. The pipeline is based on initial deep learning-based pancreas segmentation. Then we use a computational anatomy method that involves registration of the segmentation masks towards a group average. And finally, we exploit the difference of each subject from the group average using manifold learning. We aim to validate our pipeline using data from the UK Biobank imaging sub-study. We show its potential for disease stratification and automated quality control. We used magnetic resonance image acquisitions from the UK Biobank to develop segmentation model based on the standard 3D unit architecture. We annotated 217 cases, of which 195 were used for training and 22 for testing. Only the pancreas volume covered by the field of view was annotated. Due to the high class imbalance in the pancreas segmentation problem, we experimented with two loss functions, cross-entropy loss and soft dice loss, though the dice model was used for subsequent stages of the pipeline. The dice model was used to predict 3D segmentation masks for 600 further subjects. Those segmentations were iteratively registered towards the group average using diffeomorphic image registration. We used the LDDMM via geodesic shooting algorithm implemented in SPM12. Note that the template images got increasingly sharper as the algorithm progressed. The output scalar momentum image for a given subject encodes the deviations of that subject from the final template. We built a kernel similarity matrix using dot products of the smooth scalar momentum maps. This kernel matrix encodes pairwise distances between subjects and allows us to use manifold learning for nonlinear dimensionality reduction. We saw during some initial exploration of our kernel matrix that pancreas volume was a strong component of our data, so we regressed it out in order to obtain a volume invariant kernel matrix. We ran PCA with 10 components on the updated kernel matrix to extract modes of variation of the segmentation masks. These provided us with a low-dimensional space where we could explore separation between control subjects and subjects with different conditions, such as fat infiltration. We believe that segmentation masks with missing portions may indicate different fat infiltration patterns in our fat-suppressed scans. So we labeled a subset of segmentations with missing portions, further identifying which portion was missing, either head or body and tail. For the results, we saw that the dice loss model gave significantly greater performance than the model trained with a cross-entropy loss, and it gave higher dice similarity coefficients in 21 out of 22 cases. These are example images with segmentation masks overlaid in our subject population. We predicted segmentations on a total of 3,909 subjects. With regards to quality control, we saw that 42 of those subjects had 0 volume reported, which was caused by imaging artifacts, with wraparound being the most common, or no pancreas coverage due to incorrect positioning. We saw a greater prevalence of high BMI cases among acquisitions with artifacts, compared with the entire population. 198 subjects had non-zero volumes, but that were smaller than 10 milliliters, due to either suboptimal coverage or poor segmentation performance. These were excluded from posterior analyses. Volume measurements allowed relative comparisons between groups of subjects. We saw that males had larger pancreas than females, consistent with previous work. We saw that overweight subjects had larger pancreas than normal weight, and that obese subjects did not have larger pancreas than the overweight population. Preliminary results in shape analysis show that upon simple inspection, using the first and fourth modes of variation showed 93% classification performance, though with no independent validation. We also observed no clear boundary between these subjects and the rest when including all data. The 2D space shown by the first and fourth modes showed potential for classification of the gender label as well. In our volume work, we placed no constraints on the choice of network architecture used for segmentation, though we observed that segmentation-derived metrics will depend on segmentation performance. We used volume thresholding for QC, but we think that specific quality control measures for outlier detection that are independent from volume should be considered in the future. The mean volume that we report is smaller than that in the literature, and we think that this is due to poor organ coverage. Now, separate acquisitions with more coverage, like whole body scans in Biobank, could be used to correct for missing volumes. However, we believe that the relative comparisons presented here is still valid, and future work should look into comparisons between groups with different conditions, such as the metabolic syndrome and type 2 diabetes. The results of this work with regards to shape show promise of such a pipeline in a fat-infiltrated pancreas population. We worked here under the assumption that missing portions of segmentations were equivalent to fat-infiltrated regions, but these only holds when we have full organ coverage and also acceptable segmentation performance. We think that shape is complementary as a biomarker to proton density fat fraction, which reflects fat deposition in the parenchyma. In conclusion, we presented a pipeline for pancreas imaging biomarkers of volume and shape, involving state-of-the-art organ segmentation and representation learning. To our knowledge, This work is the first to attempt learning the pancreas morphology instead of using subjective scoring or hand-engineered features. This is our first step towards the goal of developing a machine learning-based approach to the analysis of pancreas state and pathology. Thank you for your attention.